Welcome to the lesson for errors, precision, and accuracy. This covers 3.3 of the Harris textbook, 9th edition. So before we talk about some math behind this, we're going to talk about some definition that we need to establish. So every measurement that is taken has an experimental error that is inherent whenever you measure something, because there's always going to be some sort of error in how you conducted it, and it's just, the tool that you use is just differs greatly depending on which measurement you have. Experimental error can be branched out to two types of errors: systematic and random errors. The systematic errors, we call this one a determinant error. It's a consistent error because there's a flaw in the equipment or because of the experimental design. This is often detected and can be corrected. So a good example of it is a student who got the wrong volumes from a pipette, right? And that is very consistent with the other ones that they got. So that's a systematic error. Another one is when, for example, you didn't tear the 3-point balance correctly. That's why you keep getting bizarre results in your math. Another type of error is random error, which is indeterminate error, which cannot be eliminated because it's uncontrollable. It's there already. And this is caused by many things like weather, and that pretty much lead into a whole lot of plethora of other stuff like moisture in the lab, or it's just the fact that it's wet, right? You cannot prevent that to happen because it's weather. Precision means that it can be reproduced, meaning if you have a measure quantity several times and the values agree closely with one another, your measurement is precise. Accuracy describes how close a measured value is to the true value. And I kind of once again reiterated is that the measured value is closer to its actual value. That means accuracy. So this is like a good illustration of what accuracy and precision looks like. So let's start first with precision. Precision means your measured values are so close to one another, kind of like here, represented as dots. Accuracy, though, which is shown right here on the third one, see how close they are to the red target. That means it's accurate. Now, the one on top is low accuracy, low precision, because they're all scattered with one another. That means they're not precise, and they're really far away from the target. That means it's low in accuracy. The last thing on the bottom right here is high accurate, because it's so close to the red target, and it's highly precise because the values, these dots right here, are so close to one another. Absolute uncertainty tells you the margin of certainty in the measurement. This is your margin of error. So for example, the calibrated of 60 milliliters has 0.02 mil of absolute uncertainty. So some formulas to keep in mind is that relative uncertainty is equals to margin of error divided by measured or known value. Well, percent relative uncertainty is just 100 times the relative uncertainty. That's why it's a word percent. Percent means times it by 100. Let's do some problems. So chemists measured the time required for a chemical reaction and found the value to be 155 plus or minus 0.21 hours. Find the absolute uncertainty. Absolute uncertainty is just this plus or minus whatever right here after the sign, which in this case is 0.21. So that's your absolute uncertainty. 2. Relative uncertainty. Relative uncertainty, I'm going to denote margin of error as ME divided by the actual or known value. I'm just going to say that it's A or K. In this case, it's just going to be 0.21 divided by 1.155. And pull up my calculator first. 0.21 divided by 155 is just 0.001355. Okay. Now calculate for the percent relative uncertainty. So this is relative uncertainty 0.001355 times it by 100. Okay. And that's just going to be 0.135%. That means we have lower percent relative uncertainty. That means the measurement that you've taken is quite accurate and precise. Okay. For problem 2, 3 1-gram weights are measured as 1.05, 1 gram, and 0.095. We'll do it this way, so it's kind of less confusing. We have 0.95 here. Then you have 1. And then you have 1.05 right here. The absolute uncertainty tells you the margin of error between all 3 of these values. So you can see the distance between this is 0.05, and same thing right here too, 0.05 as well. Therefore, your absolute uncertainty, which is your margin of error for all 3 values, 0.05. Relative uncertainty must be your margin of error divided by your actual value. I'm just denote that as ACV. And that's going to be 0.05, so that's our margin of error, divided by our actual value. Our actual value here is 1 gram, because that's the actual weight, right? That's 1 gram is our actual. That's just going to be 0.05. Right, on the last question, they're asking you for the percent relative uncertainty. So 0.05 times 100, so it'd be 5%. So we have 5% relative uncertainty on these weights.